नहीं वो फुल स्क्रीन नहीं आया ना. Yeah, welcome learners. In this today we shall discuss about the concept of graph complement. And in the previous sessions we have discussed about the concepts like connectedness, diameters, and we shall see here that how the concept of graph complement is related to the concepts of connectedness, and then we shall see how to find the diameter of the complement of a graph in terms of the diameter of the graph itself. So, basically we shall only discuss about three concepts: the complement, the graph complement, and then the connectedness and complement, and then the relationship between diameter and complement. So, we start with the definition. The complement of a simple graph G is the graph G bar with the vertex set the same as the vertex set of G, and the edge set consisting of all those edges which are missing in G. Now, here it requires a little clarification. The edges which are missing in G means you just consider the complete graph with the same vertex set as G, and then you just look at any two vertices U and V, and if U and V are not adjacent in G, then those vertices would be adjacent in G bar. For instance, just look at this graph K6 shown here, the complete graph on 6 vertices. It has 6 vertices and 6 choose 2 edges, right, which is the maximum number of edges in any simple graph on 6 vertices, right. So, there is no edge missing here, all the edges are present, and therefore, in its complement, that is in K6 bar, we can see that there is no edge. All the vertices here are isolated. So, in fact, for any complete graph, the complement of that is a null graph. You can see that it is a null graph. Now, look at the graph G here. It has 4 vertices and 4 edges. So, there are 2 edges missing here, namely U2, U4 and U1, U3. So, these edges are the part of G complement, right, U2, U4 and U1, U3. So, if you just take the union of a graph and its complement, what you will get is the complete graph with the same vertex set as G. Now, let us look at a very fundamental result about complement. It says that if an n vertex simple graph G has size m, then the size of G bar is n choose 2 minus m. Now, in other words, it means that the size of G, the sum of the sizes of G and the size of G bar equals n choose 2, the size of a complete graph on n vertices. The result is straightforward. We know that G bar has precisely those edges which are missing in G, right. So, if you just take the union of G and G bar, what we get is a complete graph which has n choose 2 edges, right, and hence the size of G bar is n choose 2 minus m, where m is the size of G. Now let us look at some questions. Let G be any subgraph of a simple graph G. Let H be any subgraph of a simple graph G. We have to see whether H bar is a subgraph of G bar or not. The answer is no. To see a counter example, let us consider this graph G. G has again 4 vertices and 5 edges. So, G complement has just one edge and the same 4 vertices. Now, let us look at some subgraph H of G shown in red vertices and red edges. Just look at the pair U and W. U and W are not adjacent in this graph, right? And hence, they must be adjacent in the complement of this graph. That means, the edge U W must be present in H bar, but here you can see that there is no such edge in G bar, hence H bar cannot be a subgraph of G bar. So, this was the case when H is any subgraph of G. However, if you just consider H to be an induced subgraph of G, then H bar would be an induced subgraph of G bar. And this is the next question. If H is an induced subgraph of a simple graph G, then we shall show that H bar is an induced subgraph of G bar. The first thing is the vertex set of H bar is subset of vertex set of G bar, right? Because the vertex set of H bar is nothing but the vertex set of H itself, and the vertex set of G bar is nothing but the vertex set of G itself. So, and we are given that H is an induced subgraph of G. So, it follows that V H bar is a subset of V G bar. Now, we shall show that E H bar is a subset of E G bar. So, we just pick any edge U V in H bar. Now, this means that U V is not present in H. Of course, U and V, the vertices U and V are present in H, but we are given that H is an induced subgraph of G, right? It means that if U V is not present in H, then U V would also be not present in G. Right? This is a property of induced subgraphs. Now, this means that U V belongs to E G bar, right. So, thus we have shown that E H bar is a subset of E G bar, and therefore, H bar is an induced subgraph of G bar. Let us look at another question. If G is a bipartite graph, then is G bar also bipartite? The question is easy and I leave it to you. Let us look at another question. Draw the complement of Peterson graph and answer the following. You can recall what the definition of Peterson graph, and you have to draw the complement of this Peterson graph and then find what is the diameter of the complement. What is the center of the complement, and then is the complement regular? This is also easy. The next question is, given any simple regular graph G, is G bar also regular? You can see that a regular graph is a graph where all the vertices have degree same, right. So, suppose you just take any vertex in G and which has degree k, then the degree of that vertex in G bar becomes n minus 1 minus k, and since that vertex is arbitrary, all the vertices of G bar also have the same degree, right, and hence G bar is regular. Okay, now we come to the concept of the complement of complement. It is natural to expect that the complement of a graph is the graph itself, and indeed it is the case. We have this result. If G is a simple graph, then the complement of G is the graph G itself. We shall prove it here. So, the first thing is the vertex set of G double bar is the same as the vertex set of G bar, right, and which is the same as the vertex set of G. Now, we have to show that the edge set of G double bar is equals to the edge set of G. So, and this follows very easily from the following argument. You just pick any edge in G double bar, right, then E is not present in G bar, right, and hence E must be present in G. Similarly, you can go backward. If you just take any edge E in G, then E would not be in G bar, and hence E would be in G double bar. So, this shows that the edge set of G double bar is equal to the edge set of G. Thus, G double bar is nothing but the graph G itself. Now, we come to the concept connectedness and how it is related to the complement. You know that a graph is connected if for any two vertices of it there exists a path that joins them, right. So, in this regard we have a result. If G is a simple graph, then at least one of G and G bar is connected. In other words, both G and G bar cannot be disconnected. Before we prove it, let us look at some examples. Look at this graph G. It has 6 vertices, and you can see that its complement is this one, because the edges which are missing here are, for instance, look at this pair, there is no edge here, and hence that edge is present in G bar. Similarly, there is no edge between these two vertices, and hence there is an edge here. Likewise, these two edges are missing here and they are present in G bar. So, we can see that here G is connected, but G bar is disconnected. Look at this graph. Here both G and G bar are connected. Look at now this graph G. Here G is disconnected, but its complement is connected. So, now we shall prove this result. So, we shall assume that G is disconnected, and then we show that G bar is connected, right. So, we shall just pick any two vertices U and V in G bar, and of course, these are also the vertices of G, but G is disconnected. So, there are two cases, either both U and V lie in the same component of G or in distinct components of G. So, first let us consider the case when U and V lie in distinct components of G. As you can see in this picture, these are the two components of G, one contains U and another contains V. Now, it means that U and V are not adjacent in G, right, and hence they must be adjacent in G bar. Okay. Now, we consider the second case. So, assume that U and V are in the same component of G. This is one component that contains both U and V, but G is disconnected, right. So, there is one more component of G, and now you just put any vertex in G, any vertex in this component. Clearly, this vertex is not adjacent to U and V, and hence U and V both would be adjacent to W in G bar, right. So, thus in both the cases we have seen that U and V are connected by a path, and which is of course has length at most 2, and hence G bar is connected. Now, we shall assume that G bar is disconnected, and then we can use the same argument we have used above to show that the complement of G bar, that is the G, that is the graph G itself, is also connected, right. So, thus we have proved that given any simple graph G, both G and G bar cannot be disconnected, at least one of them is connected. Now, there is a simple corollary of this theorem. Let G be a disconnected simple graph, then the diameter of G bar is at most 2. We have just seen that any two vertices in G bar have a path of length at most 2, and therefore, the distance between them is at most 2, and since U and V are arbitrary, the diameter of G bar is at most 2. Now, let us look at some questions. Does there exist a graph G such that the diameter of G and G bar both equals 1, equals 2, or equals 3? So, we just skip the first two parts, these are very easy. Let us look at the third part. So, we have to we shall construct a graph G in such a way that the diameter of both G and G bar is 3, and such a graph is P3. You can see that P3 has diameter 3, right, and the complement of P3 is this one, and this graph is essentially P3, and hence its diameter is also 3. Okay, now we come to the the main result of this session. If G is a simple graph with diameter at least 3, then the diameter of its complement is at most 3. So, what we are given? We are given that the diameter of G is at least 3, right. Now, this means that G has at least two vertices, say U and V, which are at a distance of 3, and we shall use this pair to conclude that the diameter of G bar cannot be more than 3. So, let us pick any two vertices U and V in G such that the distance between them is equal to 3. So, let P be a shortest UV path of length 3. Note that the internal vertices U and internal vertices on this path cannot be adjacent to both U and V, right, because otherwise this UV would be having a path shorter than P, right, which contradicts the hypothesis. So, U and V are non-adjacent here, Likewise, there is no edge of this kind and no edge of this kind. So now let's look at how does this path looks like in the complement of G. So this is the complement of P bar in G bar, right. Here U, V are non-adjacent, so U and V are adjacent, and likewise this edge is not present here, so this edge is here, and similarly this edge is absent here, so this edge is present here. Now you just pick any two vertices, say X and Y in G bar, then those vertices would also be in G, right. So if both X and Y lie on this path, then the distance between them is at most 3, right. We can see that any two vertices on P bar are at a distance of at most 3. Now consider some vertex X is not on this path, and let Y be any vertex on this path. In that case, what happens? Since X cannot be adjacent to both U and V here, right, because the diameter is at least 3, diameter of G is at least 3, right. So X cannot be adjacent to both U and V, and hence X would be adjacent to at least one of these two vertices in G bar. For instance, suppose X is adjacent to U. In that case, for any vertex Y on this path, the distance between X and Y would be at most 3. It cannot cross 3. Now let us look at the case where both X and Y do not lie on this path P. Now what happens? As in the previous case, X is not adjacent to both U and V, and similarly Y is not adjacent to both U and V, and hence it means X is adjacent to at least one of U and V, and Y is adjacent to at least one of U and V. For instance, just consider the case where X is adjacent to U and Y is adjacent to V. So in that case, X and Y are connected by a path of length 3, right. Similarly, if Y is adjacent to U and X is adjacent to V, in that case also X and Y are connected by a path of length 3. Now consider, suppose both X and Y are adjacent to U, in that case the X and Y have a path of length 2, and similarly in the case when X and Y both are adjacent to V, in that case X and Y are connected by a path of length 2. So in all these cases, what we have seen is that the distance between X and Y is at most 3, and this means, since X and Y are arbitrary, this means that the graph G bar has diameter at most 3. So this is very important result that relates the diameter of a graph and the diameter of the complement of the graph. Now there is a nice corollary of this theorem. It says that if G is a simple graph with diameter at least 4, then the diameter of its complement is at most 2. It is easy, you just use the method of contradiction. You just suppose that the diameter of G bar is not less than or equal to 2, then what happens? Diameter of G bar is not less than or equal to 2 means diameter of G bar is greater than or equal to 3, and hence the diameter of G double bar becomes at most 3, right, and which contradicts this hypothesis, because we are given that diameter of G is greater than or equal to 4. Now, there is an important lemma. Let G be an n vertex simple graph and let V be any vertex of G, then the degree of V in G plus the degree of V in G bar sum to n minus 1. And the second one is the minimum degree of G plus the maximum degree of G bar equals n minus 1. So, these results follow easily. You just consider the vertex V and let V has k neighbors in G, right, and then n minus 1 minus k vertices are non-adjacent to V. So, these n minus 1 minus k vertices are the neighbors of V in G bar, and hence the degree sum of V in G and G bar becomes n minus 1. Now, let us consider one question. If G is an n vertex simple disconnected graph, then show that the maximum degree of G bar is at least n by 2. You shall use the method of contradiction here again to prove it. So, you just assume that this is not true, that is the maximum degree of G bar is at least is at most n by 2 minus 1, right. Now, this means that the minimum degree of G becomes at least n minus 1 minus this one, maximum degree of G bar, right, and this quantity becomes equal to n by 2. And you know that if any graph has minimum degree at least n by 2, then that graph is connected. So, this is a contradiction, because we have assumed that G is disconnected, and hence the maximum degree of G bar is at least n by 2. Now, let us look at the last question. If a simple graph G has at least 2 leaves, then G bar has at most 2 leaves. You can recall that a leaf is a vertex of degree 1. So, here we are given that a simple graph G has at least 2 leaves, and we have to show that G bar has at most 2 leaves. So, we just consider any 2 leaves x and y of G, and let u and v be the vertices in G such that x is adjacent to u and y is adjacent to v, right. Look at this picture. X and y are the leaves, 2 leaves, and u is adjacent to x and v is adjacent to y. Now, let us look at how does these vertices look like in G complement. So, this is the situation in G complement. If x and y are not adjacent here, then they would be adjacent here, and since the edge u y is not present here and u y is there. Now, you just consider any vertex apart from these 4 vertices. If a graph has only these 4 vertices, then there is nothing to prove here. So, suppose there is some one more vertex, say W in G, then W is not adjacent to both x and y, right, and hence W would be adjacent to both x and y here. Similarly, you consider any vertex here. So, all the vertices in G bar except u and v have degree at least 2. So, the only 2 possible vertices for leaves are u and v, and that proves that G bar has at most 2 leaves. So, in this session, we have covered the concept of graph complement. We have seen some examples of graph complement. We have also then discussed about some relationship between the complement and connectedness and the relationship between the complement of a graph. And finally, we looked at how the diameter of a graph and its complement are related. So, in this session, we stop this session here. To learn more about, you can refer the book Douglas West, Introduction to Graph Theory. Thank you. Rajesh.